So, hello everyone. Today we will be talking about delay and dead time. I have actually published week 7 and 8 in YouTube. Hope that those videos are helpful. We will pick up on week 9, delay and dead time. As far as I remember, I have to check this information. I have planned 11 weeks. So this means that week 9 will be this week 10 will be next week, and the week after next week will be the last session in terms of laboratory sessions that are planned. Then we will most probably have a final session where we solve some questions. And in terms of homework 3, it should be close to its due date, as far as I remember. I guess 3 weeks is also not enough, I guess, but we will extend the due date on that, so there's no problem for that. So let's dive into week 9, delay and dead time. Up to this point, in the previous weeks, we had the PI/PD controller and we had some anti-wind-up systems that you should most definitely check out. Here in this week, we will be focusing on delay and dead time. So up to this point throughout the semester, we have assumed that if we apply certain input to systems, that the system immediately reacts and has a response, or that we have some zero lagging systems, no measurements lag whatsoever. But that's, of course, not the real world case. If you think about maybe some heavy duty vehicles, if you pull the brakes on that vehicle, it will not immediately stop, or the velocity will not drop down immediately to 0. That's something that doesn't exist. It's not immediate in that term. Therefore, there will be some time in order to end up in that state, and that's called a delay, or if the system does not react instantly, if it has some response time, that's called dead time. So it depends on the view, or if it's a system thing or if it's a thing that happens later. Both are basically interchangeably used. So yeah, and we're using the Laplace shifting operation here to talk about delay. So let me just quickly see if I can find that for you. The shifting property of Laplace. So that's what I'm after here. Let's see. Do we have a nice explanation for that? Yeah, where is it? There we go. Here I have that. Now, the shifting property basically adds an exponential term here. If you shift it in the Laplace domain, you will have that. There's also the time domain shifting property. I'm not sure if it's shown here. There are two shifting theorems. One of them is in the time domain, but the same applies for the Laplace domain. I couldn't find it for some reason. Where is it? So if we shift in time, that should be basically it, but I'm not seeing it for some reason. But you get the idea. If we shift in time, so instead of having yt, if we have yt minus 2, for example, then what you do is you basically multiply with e to the power of minus 2s. Then 2 seconds will be basically the delay part here. But of course, adding an exponential term to our transfer function definitions messes up most of the things that we have used upon the systems, because it's not going to be a linear system in terms of the terms here, because this is not a linear term here. So yeah, that makes us life even harder than it is already. So how can we define the system in MATLAB? How can we look at the step response of such a system? Well, basically what we do is we use a property here. So I've defined GS here. And if I want to have some pure delay here, what I do is I just define a transfer function that has no meaning. Basically this one here. So GSD is basically just the static gain 1. What I do here is I just add basically an input-output delay. And well, there could be some state delays, and we can use some state space representations in MATLAB. So that's the reason why we call it the input-output I/O delay, because it's between the directly the input and output. So we specify the amount of delay. In this case, it's 2 seconds. Now we will have basically a pure delay transfer function that we can use with most of the control system toolbox functions here. And if I multiply these two together, GS times GSD, you don't have to separate them. I'm just doing it for the sake of explanation here. Of course, we need to run this here. So run it. You can see I have 12 divided by s squared plus 10s plus 24 times e to the power of minus 2s. And why we call it the shifting property here, when we shift in time with minus 2 from the signal processing or signals and systems lectures, what you might remember is that we have this unit step function here, which is basically u is defined as this one here. If this is positive, then it's basically 1. If it's not, then it's 0. So if you look at this signal here, what you can see is basically if t is not greater than 2, then we will not have a response. This corresponds to 2-second delay because it waits until time hits 2. Then we have 1, and then it remains 1. So basically, this is how we approach time delay in the time domain. And if we take the Laplace transform of this, we see that an exponential term arises naturally due to the integral and e to the power of something in the Laplace integral. So let's move on. Now, we can basically use the step function here to simulate such systems, and nothing changes. Basically, you can just use it as you were using step all along. Hope that MATLAB also plays with us. There we go. And the only thing that you can see as the difference is basically a 2 seconds of shifting, nothing else. So what we can do is we can basically call this red and copy this and give it a black color here, get rid of that, and compare the non-delay and delay transfer function, which is basically the exact same transfer function, but one where GS has no delay in it, and we've added 2 seconds of delay. And you can see that there is basically a time shift. This is the same response. It doesn't change anything. The only thing that changes here is basically this shift. So you might expect that if I put in something like e minus 2t to s into the transfer function here, it might mess up the response. It does not, because it is the shifting property and it's just shifting. So therefore, we can have such transfer functions, but working with them in terms of control design, in terms of stability analysis, is not that easy. Even though the step response and stuff seems to be easy, those analysis and synthesis tools sometimes don't work even for delayed systems here. So in order to approximate this, what we can do is we can maybe use the Taylor expansion formula, etc. But we have a better approximation for delayed transfer functions. And the reason for that will be obvious at the end of the day, I hope. But this is a way better approximation method for increasing order, of course, than using Taylor expansion or other stuff like that. Because you have a nonlinear term, what you might do is you might open e to the power of minus 2s to its expansion and take some terms and then try to use that as a transfer function. Of course, it's not impossible, or it's not maybe the worst idea, but putty approximation proves itself to be more useful, and we'll see how. Now, if we have this, and if we try to look into the closed loop, then stuff gets a bit weird. And by weird, I mean the following. Let's assume a certain transfer, P controller, for example. Let's have 1, and let's look at the feedback of GSD. We have also K, comma 1. So that would be basically TS with some delay in it. So let's see what we get here. So this is TS, and yeah. We see MATLAB opts for the state space representation. Let's force MATLAB to show us the transfer function. And then you cannot even see the transfer function representation anymore, because state space models with internal delays cannot be converted into transfer function form. But you might ask yourself, I didn't do anything. I've just added the delay and a certain controller and took the closed loop. But why does it show me that? And why is it an internal delay, etc., etc.? So, well, at this point, what you might try to do, which seems to be a bit better, is to convert this whole thing into maybe symbolic expressions, and then see what's really going on. TF to sim, I take this part here, and GSSD, maybe something like that. Or let's have GSSD. That would be x minus 2 times s, which is not a big deal. And then we would have basically TSS, and we would calculate this. So K was 1, so let's say K equals 1. And then K times GSS times GSSD divided by 1 plus this. Let's show it, and let's simplify the fraction here to have a nice result, hopefully. Now, this is the result. And we can see that if we, for example, factor out e to the power of 2s, it would be 24 plus 10s plus s squared plus 12 to the 12 times e to the power of minus 2s, and then 12 e to the power of minus 2s. So yeah, MATLAB handles stuff differently, but as a result, we have a thing that is not a polynomial anymore. So our biggest issue with this is that if it's an open loop, if you just added an IO delay, then you're probably just shifting, so it should be a big deal. But if you try to add a controller and add a feedback structure to this, then you end up in having a nonlinear transfer function, which is not a polynomial, which is this thing here, for example. So therefore, it's not really easy to analyze closed loops and synthesize even closed loops, because we were relying on the dominant pole placements. We had some zeta and omega n. We were choosing those as dominant poles. We pushed the residual poles and zeros away. But here, we cannot use the algebraic method, which just equates stuff to each other, because we cannot handle this e to the power of 2s or minus 2s, because it's not a polynomial, and everything kind of loses its meaning. The best we do at the moment is to try to use an approximation instead of the actual transfer function. So what we will do is we will kind of take the Laplace or Fourier domain transform kind of route here. So this part is important, Fourier. When you use these two methods, which are basically almost the same, what you do is you start with a time domain, you go to the S domain, You do some stuff. Let's design, analyze, do some stuff, and then you return to the time domain, and you have basically accomplished something that was not possible in the time domain to time domain. So that's basically the whole idea in engineering when we use Laplace and Fourier transforms in filtering systems and doing stuff like that. What we are going to do using the approximation method is also the same. We have a nonlinear TS closed loop. So we will approximate everything, use approximation PADI, and again, analyze or synthesize stuff here, and then return to the actual nonlinear TS. So this part is important. Sometimes when you do some homeworks, if you're in an exam, or generally if you're trying to design a control system, what you do is you just skip the last step here. You sometimes forget to return to the actual system, return to the nonlinear TS. So keep in mind that since you're using an approximation, there will be some gaps between the actual model and your approximation. And you're doing an optimistic thing by approximating that, hoping that that is a good approximation. You just go ahead and design your controller or analyze your system. Once you have the results, when you're validating the approximation itself, it doesn't make sense. You cannot analyze the system using only the approximation because you don't know how good the approximation is or how well that approximation represents the actual system. What you have to do is you have to return to the actual system with delay, plug in your controller, for example, and see if it works, or plug in your stability condition and examine the actual system. So this is a tool that I'm going to show you here. The PADI approximation is a tool where you have a domain, you're changing the domain, solving the problem, and returning to the original problem. That's really important here. So, and that's exactly what we are going to do. We are going to use the approximation. Now, here's the formula. And what we can do is we can just use this formula in order to come up with this approximation. So let's call it PADI1. And let's define the transfer function. So minus 0.5 times 2 and 1. And then 0.5 times 2 plus 1, because here tau is equal to 2. So this is equal to 2. Actually, it's minus s plus 1 and s plus 1, but I'm just going to write it down like that. So since I've defined it in the transfer function or as a transfer function object, I might as well just go ahead and define it as a symbolic expression here. So times s plus 1 divided by the exact same without the minus sign here. So now I'm interested in the following. Let's take a look at this approximation and let's see the step responses, the pole zero maps, etc. Let's see how well I can use GS as this nonlinear form here or with an approximation. So actually, instead of doing this route, what we can do is we can also use MATLAB, and I'm going to do that in a second. But let's start with this. So first of all, let's create a figure. And let's actually look for the step response of GS times GSD. So this is the original system here. And then we will have the first order PADI approximation, which is basically a G PADI1 here. So I'm going to get rid of this. Maybe the whole symbolic stuff here. I don't know, let's keep it simple. Of course, I don't remember how many seconds we need for that. Well, it seems like, well, 2 seconds there. Let's have 5 seconds. Seems to be a good number. The second order Putty approximation, of course, adds another term, t squared divided by 12. So 2 squared divided by 12 should be that. And let's also add the second order approximation here. Putty 2. Oh, we didn't add it properly. I'm sorry. So there we go. That makes more sense, I guess. And let's plot t comma y and leg line with 2, maybe a display name of delay, and then t1. Let's have red, putty 1, putty 2, blue. There we go. So X label T, Y label YT, and then title putty approximations versus system. I don't know. So let's see. There we go. Now, when you're if you're sometimes bothered with this legend being in the way, what you can do is just a quick side note. You can do location and then best, so it avoids to place that legend. So it places it somewhere empty. So yeah. Now we have this approximation, and well, the interesting thing is the following. If you think about linear systems, even if you have an approximation, so let's see what GS times GS putty 1 is, for example. G putty. If you look at this system, there's no way that this system cannot respond, because it is not a system with delay. It's just an LTI system. At t equals 0, when you apply some input, it will respond. And it is really hard to approximate a system when you have this phenomena. So when you have a system that does respond, and another system that has delay in it, and it takes some time to respond, then approximating that system is not that simple. And you can see that the approximation looks awful. In terms of time domain data, in terms of transients, it's awful. And the reason behind that is exactly this approximation here. But you can also get the idea here. For the red one, you can see that you have a minus 0.2 peak value here. And you see that it drops down to the negative part here. So it's an undershoot, basically. And then it returns to 0. And then it reacts like the system itself. And we can say that the actual delay, the amount of delay, seems to be this value here. So instead of modeling 2 seconds of delay, with the first order approximation, we've actually modeled 1.12 seconds roughly of delay. And during this modeling here, what we've done is we have just basically wasted some time using some undershoot. So that's how we kind of approximate this transfer function using the Pareto approximation. And if we look at the blue one here, so let me delete that one here. The blue one doesn't undershoot, but we have a slight bump here towards 0.1. And then we have this reverse bump here. And then we are basically starting at 1.55 seconds roughly. So we're using these waves or bumps in order to just drive the system to a certain way, drive it back to zero, and then start acting like the system itself. So that's kind of the behavior that we're trying to use in order to model the whole thing here. And if we increase this, the order of the Pareto approximation, then things get even more clearer. Before I do that, I'm going to also show you the pole zero map side by side. So what we can do is we can just go ahead and use subplot here, CLA, and then also have some pole zero maps. Zeros. We don't need legends anymore. Pole zero map. There we go. And then we have PZ map of GS times G Pareto 1. So this is 1, this is 1, this is 2, this is going to be 2. And there we go. Now I'm going to plot real values of poles, imaginary values of poles with, since it's the first one here, red, and line width 2, should be 1. This should be blue. Now, you can check for yourself, but PZ map here actually works a bit different than you might expect. Therefore, I'm not even using that. Oh, actually, let's use it and let me show it that way. So let's call it poles. Poles. By the way, we also need the zeros here. Should be like that. And then let's have poles. Let's have that. There we go. Yeah. Let's run this. I forgot to add that. So there we go. Now we have the poles and zeros, and you can actually see that there are only 2 poles. One is at -4 and the other one is at -6. And you can immediately see that the poles belong to GS. And GSD is not given in terms of poles and zeros. It's also not possible to get them as poles and zeros. So you can just get the minimum phase part, which means that GSD is not minimum phase. And when you multiply that, your transfer function is not minimum phase anymore. So the minimum phase part, so PZ map returns just the minimum phase poles and zeros and nothing else. So it is used to separate basically the non-minimum phase part here. So it's not the only poles of the system. Neither is it the only zeros of the system that are shown here. So they are missing basically. And theoretically, what we the amount of poles and zeros are kind of infinite here because we have delay, and it's just, if you think about the approximations in a minute, you'll see why. So using the first order approximation, the body approximation, we add a pole and a zero, which is symmetric. With respect to the origin, of course. And if we have a second order, we add two poles, which are stable, by the way, but two zeros on the right half plane. And this right half plane zeros are causing basically this behavior here, which we use to waste some time to model the delay of the system. So yeah, instead of using this approximation formula here, what we are going to do is we are going to use basically PADE, which is a function in MATLAB. In the control system toolbox, you can just use PADE, provide the system the order, and it will give you basically the transfer function that you are looking for. So instead of doing this like this, what we can do is we can just use it like the following. We can just say, okay, we'll have some PADE response here. And instead of using this, we're going to use GS times GSD, which is the actual transfer function. And then, for example, 1 here. So let me get rid of the unnecessary data here. So, by the way, let me just create the handles here. So that I'm going to just use AX1, comma that, and AX1, comma that. So let me just replace them. So here we will just have the actual system. Here again, the actual system, get rid of this. Move this here, down here. Then move this here. And get rid of this. Of course, AX2, AX2. So what I'm going to do is I'm going to open up a for loop for the order here, let's say 2. And then end. Now here I can change this into a string. Plus string. Okay. So there we go. Let's call it TP, YP, Z zeros, false. Of course, I'm not going to give it some color, but then again, we might want to give it a color. Yeah, let's have a vector 1, 2. Let's have I from 1 to length k vec. And instead of using, let's use kval, k vec I. Now the order will be kval. And of course, the string will also be kval. Once we have that, what we can do is we can just generate a color. So instead of having that, let's provide a color. Let's maybe use blue for it. So then we get a transitioning from a certain color. So a tone of blue, basically. So I'm just going to provide that. There we go. Now let's see if it works. There we go. Of course, it's not really helping us here. Did we mess up stuff here? 1 and 2. The response look correct, but I'm not sure about that. About the poles and zeros. -4, -6, -1, 1. But, oh yeah, of course. Sure. So G approx maybe the transfer function, let's call it that. Let's use putty just once. K-val, and then our transfer function is basically G approx here. The reason for that is I've just these here. Let's get rid of them. Let's run. There we go. Now, of course, if we have only 2 values, it doesn't make sense. Let's keep increasing. For example, 4. Now, we see that actually the time-wasting strategy here for putty 4, which is the brightest one here, you see that there's 1 bump, 2, 3, 4, and you can see that this point where we reach 0 at the end and then behave like the system, you can see it is kind of going towards 2 seconds here. And you can also see that the peak values of these bumps are decreasing now. And ideally, what we would have is a response where we are wiggling around this 0 axis here up to 2 seconds, and then we drive the system like it should normally do. Now, it's also interesting to see, and let me just fix that for you. Let me just give it 4, so we can see the actual poles and zeros of order 4. So this is putty 4, and you can see we have 4 bumps, and the transient looks more like the original system here, even though the 0 axis is not. And we have a bunch of poles and zeros. Now we have 4 poles from the putty approximation and 4 zeros from the putty approximation. So, what happens if we increase it even further? Let's have a 10th order approximation. There you can see that there's a certain strategy. We have more wiggling around 0. We have an almost exact transient. And we have 10 poles and 10 zeros. 10 of the zeros are on the right half plane. 10 of them are on the left half plane. And we can do this all day long. You can see it's almost perfect now. We still have some bumps here, but the peak values are basically reducing down. So as I've told you before, we're just waiting around this. We just go up, go down, go up, go down, go up, go down, until we have wasted 2 seconds, and then our actual transients come into place, and we see we are basically on the trajectory here, on the original trajectory here. So we can still further increase this, but the problem is the following. The approximation looks really bad. In terms of complexity, we're out of our minds. We are not able to use this in terms of a transfer function for design or analysis. Well, we can use it for analysis, but I wouldn't recommend you to use it for synthesis purposes, because it is way out of its well, it's too complex to handle. Yeah, and this is also the reason why we theoretically speak of infinite zeros and infinite poles for a system with delay, because we're basically thinking about the putty approximation here, and we can say that an infinite pole 0 pairs correspond to the perfect line, and it starts from 0. So we have not finite amount of poles and zeros for a system with delay here. So, yeah, let's calculate the stability interval of a p-type controller using first order and second order Putty approximation using the intervals. Well, let's do it. Now I'm going to stick with this here. So let me just do it for the first two orders here. So what I'm going to do is I'm going to do the following. So sims s. Since we have gapprox and since I have tf to sim, I'm just going to call it tf to sim for me to convert that into the symbolic expression. I am going to have k, which is a real value. I'm also going to have omega, which is also going to be a real value. And the closed loop for a p-type controller here would be k times gss, and then 1 plus k times gss. I'm more interested in the characteristic polynomial, so num then. I'm omitting the numerator here. We have that. Now, I'm going to substitute into PCS the characteristic polynomial. Instead of s, I have 1i. The problem that I'm going to solve is basically the real value of p omega should be 0, and the imaginary value of p omega should also be 0. So the idea behind this method here is the following. If I have a certain polynomial, which looks like this, if it's satisfying j omega, so 0 plus j omega basically, it has no real value and it's a pure complex value, imaginary value. And if it's equal to 0 plus 0j here, it means that I'm on the j omega axis here. So this is quite important because it is a complex valued function, a polynomial, because I'm plugging in a complex value. So the real part should also be 0. The imaginary part should also be 0. If that's the case, it is satisfying the polynomial, which means that it is a root of the polynomial. And if it's a root of the polynomial, I'm interested in it because I want to look at it, which k value is causing this, because that k value is causing a j omega crossing or the marginal stability here. Therefore, it's going to be my stability bound. Therefore, I'm just solving this problem. Let me see what the solution looks like in terms of k and omega. So if basically multiple values here that we're solving here, k starts from 1 to 2, so one of them is k, one of them is omega, and I need to get rid of some omega values. So let's call this, let's call it kv and omega v for values, but we have used kval or kvac. So let's also convert it into double. There we go. Now, I'm interested in the indices where omega val, since we've called it real, so there will be no problem with that. So where omega val should be greater than or equal to 0 here. Let's eliminate the values that we are not interested in. Like this. Let's see kv and omega v again here. So we have basically this one here, -2 and 2.43, 0 and 219, and then -2, 216, -354, and 0 and 1.35. So yeah, let's see. If k is greater than -3.5, it is also greater than -2, but the actual bound then would be -2. So the stability interval starts at -2 here, basically. And the upper bound is 2.16. So let's call it kvp for positive values. And so let's take the index here. Let's say kv greater than 0, greater than or equal to maybe. Yeah, let's have that. Let's have kvp here. So positive values of KV. I'm not that interested in that. In omega, I'm more interested in KV positive values here. So let's have index here. And index not here maybe. Or let's actually have that. Let's say KV positive. Let's say KV negative here. And I'm going to basically display a certain string here. And it would be the maximum of KV negative here, if I'm not mistaken, K, and then this, and then, oh, this should be inside of string, plus that, plus string, and then the minimum value of KV positive, I guess. So let's see. Yeah, now we can see basically what I've done. I have just shrinked the, or I've just eliminated the upper bounds that are not really upper bounds because we have to end all the conditions here. And there are multiple j omega crossings here, as you can see. At this point, it's not that big of a deal. But if I increase the value up to, for example, 10 here, you will see that it kind of changes basically the intervals here. I'm not sure if this is going to be an issue or not. For 10, we don't get 10. Why is that? Did we mess up something here? I'm not sure. Well, in the 10th approximation, for some reason, we don't get the values, or we're not. There are only 4 printfs. I'm curious about the current KV here. Maybe, interesting. At some order, we have even issues to solve it. Maybe a solution is not available. Oh, there's just one solution there. Interesting. Why is that? Let me see. Let's call it 10. Let's call run 1. Solution, problem, VPA. Even MATLAB is not coming up with the solution, I guess. So, yeah. It did come up with just K and omega, so I don't know why that is. But if we would have looked at the root locus plot, we would see that a transitioning from here to here. So there will be a crossing here, another crossing here, another crossing here, here, etc. So it's not really that important at that point because we will have lots of j omega crossings, but we're interested in the minimum k value during the crossing here for some j omega value. And for 0, there's basically just 1, so that's not that big of a deal. So that's the reason why we have better bounds for low values, for the negative ones. We have just the best approximation there. But you can see another thing here, namely that if we have a stability interval here, the upper bound is basically not the correct upper bound here. What I mean by that is the following. If you have the first order party approximation, you would assume that lower values than 2.43 makes the system stable. Well, it does make the approximation stable, but not the actual system. You can pick 2.4 and look at the step response of the closed loop, and you will see what I mean by that. We can just have another figure, look for step feedback of 2.4 times GS times GSD, comma 1, and you'll see what I mean by that. So let's run this one here. Let's have that, and you can see it's not stable. Whereas the approximation itself seems to be stable, the system itself doesn't have to be stable. So it means that the actual system is not kind of obeying the same rules or properties of the actual system because it's an approximation. We don't have a guarantee for that. So what we have to do is we have to use the approximation and check the original system back. So that is what I mean by using the Fourier or Laplace transform kind of route here. So you see that the approximation is stable. Okay, that's good. But is the actual system stable? That you have to test. Since you have an upper bound, you can see if it's stable or not. So we can basically try 1659, the next approximation here, and see if it works or not. So yeah, it seems like the zeta value is improving. The oscillations become less bad, but it's still unstable. So 1659 is still not the bound that we are after here. It seems like 1532 should be a good one, but still it's not guaranteed here. You can see it's almost at perfect oscillation, which means that if I drop the 32 bit here, so if I call 15, we should be in better shape. So now this is kind of very bad but stable, so we can see that 2.15 is a nice approximation in terms of stability. So we couldn't use root locus for our system here because it's not possible to draw a root locus for this kind of system. And the reason behind that is infinite amount of zeros and poles. You have to place all your finite poles in zeros, but you have infinite amount of them. So yeah, it doesn't make sense. But you can use the approximation and then plot a root locus. Well, that would result in the root locus using one of these approximations. So yeah. Now, what about designing a controller for such a system? Let's talk about that. Well, as you might expect this, we are going to design a system to the approximation. Let's quickly do that and let's see. We have a PI controller. So let me just define a new, open up a new script here. Just quickly do this. So let's have basically GS and GSD here. And then we need basically the symbolic expression here. But we will use this here. So sims S and sims KP and KI, these are real values. Let's look at the following, where FSS is KP plus KI divided by S, and TSS is basically FSS times GSS. This is quite the usual stuff here. So 1 plus this, and PZS, PCS is num than TSS here. Now we also have some overshoot and settling time values, 10% overshoot, and nothing else, I guess. Yeah, so OS is 10%. So zeta is minus log overshoot divided by the square root of pi squared plus log overshoot squared. There we go. Let's have omega n. So let's see what the order of this system is. This is also real value here. PDS is 2 times theta times omega n times s plus omega n squared. So let's run that. We don't have kval because let's use the first approximation here. We don't have GSS because it should be GSS is equal to TF to sim G approx. There we go. So run 2, so we have TCS. Now it's a 4th order transfer function, which means that we need a 2nd order s squared plus a times s plus b, where sims a and b are real values. So the problem then would be to equate coefs PCS as all coefficients to coefs PDS PS, and then the solution would be found with this. So let's see what the solution looks like. 1, 2. Let's see. Why don't we have a solution for this? Interesting. Maybe it's about 10%. I don't remember. What is the problem actually? Oh, we have a minus. Okay, now. Instead of using PCS directly, what we have to do is we have to have a slight normalization going on. So pole equals pole divided by pole, the first element, and then use pole instead of PCS. Because of the approximation, we will have negative signs. So, yeah. Now we have a solution. Solve B. I'm checking A and B. If they're positive, it is a solve omega n. Well, it seems to be stable, but omega n is equal to 0, so that's not nice. So it seems like we still have some issues here. Maybe increase the overshoot a little bit. I don't remember the solution, so let me just try that. Sol.A, sol.B, sol.omega n. Didn't I update this? Run to. It's not changing, I guess. Yeah, it's not using KI term. We again need to look at the problem here. Why is this happening? All right, we have A, we have, maybe we have too many unknowns. That's maybe the reason here. So 1, 2, 3, 4 equations. We don't know what A, B, K, P, K. Of course, that's it. So let's basically choose just the settling time here, because this is an example. Theta times TS. Therefore, it should be this. Omega n. And TS should be equal to, I don't know, maybe 5 seconds. Yeah, it seems like we have a good solution here that we can work with. Of course, we have to optimize it in terms of 0, in terms of dominance, but that's not really the idea here. So let's define the controller here. Ki val, sol.ki. Fs is going to be Tf. Kp val, Ki val. Now, at this point, I'm going to have Ts, which is going to be feedback, and G approx, and then we have Fs times G approx, comma 1, and then have a step response here, and see if it's working or not. So we have this step response here. So it has a bump, but it seems to have a certain overshoot. It's not looking like 10%, but yeah, we can look at the pole zero map and understand why that is. But this is not the actual response that we should see. And the reason behind that is basically, let's call this, let's have a blue color for this. We should actually look for the system with delay. And this is exactly, again, the point that I'm trying to make, because the actual transfer function is not gapprox, it is gs times gsd. So it should have delay in it, and we should see basically the effect of delay somehow. And now we can see that the responses of the actual transfer function and the approximation are not quite the same. You can see there's more than 20% overshoot in terms of the system behavior, and you can see that there should always be a 2-second delay here. And the reason for that is because the system, it doesn't matter what you do, doesn't respond for 2 seconds. So if your closed loop step response doesn't have that delay effect, if it's responding immediately, then you're probably looking at the putty approximation, not the actual system. The actual system has delay, and you should see that in your closed loop step response. If not, then you have something wrong going on. And you can see that the first order approximation here doesn't really do a good job. Let's see if the second order approximation here helps us out a little bit better. So let me just copy and paste stuff here from here. So let's call this FS1, TS-approx1, FS1, TS1. So this is the first order approximation. And yeah, this should be it, basically. Let's have second order putty approximation here and copy and paste the stuff. I guess this should be good to go. So again, here I'm using the TF to sim, so I'm not really bothering with that. Now here it would seem like I need to add another pole here, and it should be s cubed plus as squared plus b times s, because if you increase the order of your putty approximation, you increase the amount of poles in your open loop system due to the approximation. So you should also have more residue poles. Now let's equate that. Let's have that. I'm only interested in this, hopefully, hoping that it should work. Let's see. Let's call it 2. Let's see if it's going to give us. Of course, we are missing some crucial steps. This is not the actual way of designing it. We are just basically just accepting some solution, not the best solution here. So it's not really fair to judge our results here, because we have to optimize them. You have to use the first order approximation, but the best suiting solution. And then your second order approximation, again, the best suiting solution. I didn't check for the dominance of the residue poles. I didn't check for the zero. I didn't check for anything. I'm just blindly doing it. So let's see what's really going on here. If we have TS1, TS-approx1, figure 1 CLF. Let's have another figure. There we go. Let's run. That's one solution. That's another solution. Well, for the second one, the approximation is way better. And I can tell that due to the similar behavior, even though the solution is not the best one. And this is exactly what I meant by not judging them fairly, because the first order approximation seems to be a better solution, but you have to optimize your solutions. So for the first part and the second part, I should look for the best dominance factor and then try to judge if this is better or not. But I can see that the similarity is way better here. So it behaves like the approximation. The only difference being this approximation bump thing about the zero axis here. But other than that, during the transients, it seems like it is almost the same transfer function. So that's quite nice to see. But yeah, these are not the optimal controllers, the best controllers that we can get out of both. But yeah, you can see that it is harder to kind of approximate this, but you have to have a certain payoff here, because if the complexity is higher, you will get a better approximation, and the better the approximation, the closer the response of your actual system will be. But the simpler the approximation, the easier it is going to be to solve it. So there's a basic trade-off there, simplicity and accuracy. So you have to make your choice. The best thing to do will be starting off with the lowest possible approximation and work your way up, because you want to increase the accuracy, but you don't want to deal with the most complex transfer function that you can see, because that's hard to solve here. So that's that part. Now we also have something called the Smith predictor, which is quite interesting and which I'm going to talk about, and then we will conclude today's lesson. Now, we've talked about the first, we've introduced basically the Putty approximation. That's quite important, but there's a special structure that we can use in order to deal with systems that have delay in it. And I'm going to show you that part out of the PDF here. But the important thing about the Smith predictor is that it has a special structure. And what it does is it does the following. Let me just append it somewhere here. Smith predictor. So what we're doing here is basically we're trying to have a model. So we have a controller here, we have the system, and then we have the exponential term. Let's call it minus 2s. Like this. Now, this part is actually the actual model of the system. Let's assume that this is an induction motor, or in our laboratory, and we're basically assigning this mathematical model to this system. But in real life, this is basically the model or the system itself in the lab. So this exists actually. Now, what we do is we basically take the signal here. So let me just quickly do that. And we add our approximation here and take the difference. So we have a summation point here. And this is basically plus, and this is minus here. So we have a minus sign here. So ideally, what you would expect out of this signal, because this is the system output itself. So this is y, the output, but this is basically y minus y something. So let's say underscore here. So this is not really an output. This is basically an error. And this difference is quite important because it will tell you the model differences. If your system in the lab has this exact same transfer function with the exact same coefficients, poles, zeros, and the amount of delay, then they will overlap. So this will also synthetically become the output itself. Output minus output would give you 0, and there will be no error whatsoever. Ideally, you would expect this one because you are modeling the system as good as possible. Then you have basically shown that this is basically your system. What you then do, again, from this point, or you can take it from here somewhere. So something like this. So we have this line here. Now we have GS, and we add that to this error here. So there's another summation point. Now what you would have is basically y without delay, a certain y. So let's call it y prime for some reason. And that causes the following. Let me just add this back here. You have basically an output value that would be the value if you wouldn't have any delay in the system. You sort of eliminated or subtracted the expected delay behavior out of your output, and you've generated your output on your own. And this solely depends on the fact that this should be ideally 0. So these should be tending to 0. Therefore, the system model should be tending to your model with delay here. If this is the case, then you have an outer loop here. So there's another summation point, there's another thing here, and you will have basically this here, an outer loop here. That basically measures the output from this exact point. So you have a loop where you compare basically your model and the system in the laboratory. You take the difference, you add the non-delay or the non-minimum phase, the minimum phase part, I'm sorry, the minimum phase part, the part which has no delay in it. You add that part, then you take that output as your measurement and feed it back to the system. You might ask yourself why we would bother with this interesting thing here. Well, the reason would be the following. By the way, this is not the output itself. Don't mistake this as the output. The output is basically here. So this is basically the output Y. This is the system output still. So it seems like this is on the feed forward path, but it is not. It's on the feedback path. So all this stuff that I have added here with FS is basically created by us. So basically, this is the whole control structure. You have the controller plus some additional structure, the difference, the system model, etc. And here you have the output. So it is important to note that this is basically what is going on. If you look at the Smith predictor notes in your lecture notes or in my laboratory notes, you will see there are a bunch of equations, and then you have GS times e to the power of minus tau s, on and on everywhere, but it doesn't have meaning. But if you know the meaning behind it, it's quite simple. We have a system in the lab, we have a model of the system, the mathematical representation. We take the difference between real life and computer. You can think about that like that. And then we add the non-minimum phase part. And we have a feedback structure, but we are still on the feedback here because the measurement data is still the output of the system. And ideally, you would have basically the following closed loop transfer function that would look like Fs times Gs divided by 1 plus Fs times Gs, all this times exp minus 2s. So this is on a feedback again. If you calculate the transfer function here, remember that this is Gs times e to the power of minus 2s. So since your feedback doesn't have ideally any delay in it, you end up in the minimum phase part controller, and then times e to the power of minus 2s. So basically what it does is it constructs an imaginary output which has no delay in it, feeds it back, and then shifts it in time with the amount of delay. That's basically it. When you're designing a controller using Smith Predictor, you're designing a controller for the non-delay part, which is basically GS on its own. And doing that is quite simple because you have GS. What you're going to do is you're just going to take this part, maybe also this one here. So let me just quickly try to do that. So we will have, again, the same code, but now we don't need this. Instead of having the approximation itself, we will have just GS. So this will be GS. We will convert GS into GSS. Try this stuff out. I expect that it should be just A, and this should be A, S plus A. And then we are going to solve it, and then let's call it 3 here. Of course, we just need the controller itself, nothing else. So let me run the script again. So there we go. This is basically our controller. I'm not sure if it's optimal or not. Let's check if it's stable at least. It seems to be stable, so yeah, no problem with that. So basically the result then will be TS equals feedback F S 3 times GS, comma 1 times GST. So it's interesting because it doesn't look like that, but it would be this result here, and you would end up in step TS like this. And this would be basically your design here. Of course, I'm just showing you the ideal output. You have to construct this whole structure here in order to see if it's really the case or not. And I have also an exercise where we change basically this system in the lab, the representation a little bit, and see if it's working and how it's working, basically. So let me just quickly show you my PDF. I have all the approximations, all that stuff in here. I have basically plotted the root locus plots in the PDF, and I've shown that the stability bound is not really the stability bound that we see. Here I have skipped even the PI design part in my notes. I've just used a random PI controller that works for some reason or has a pole zero cancellation, something like that. And I've just shown you that the approximation is somehow similar. But here we have basically the structure transfer function in more detail. So this is basically the assumption that you have a G0 part, which is the minimum phase part, and then the delay part here. By the way, minimum phase means that the system and the inverse of the system is stable, which translates into all the poles and zeros should be on the left half plane. If you have a right half plane 0 or pole, it's not a non-minimum phase anymore. It's not a minimum phase anymore. It's not minimum phase. The reason for that is that the system zeros and poles change if you take the inverse. So it's kind of a theoretical way of saying that all the zeros and poles should be on the left half plane. And the Putty approximation doesn't result in minimum phase parts because it's adding zeros on the right half plane. Here we have the non-minimum phase part, the minimum phase part, I'm sorry, times the delay part here. And what we're doing is we're basically looking for the inner feedback loop, the controller and the model, and then we have the next branch, and then the next outer loop. So this is kind of the structure that I've. Do I have a? Well, I don't have basically the structure shown here, but you can look the structure up, or you can try to sketch it on your own even. But you can see here we have basically the steps. You can just follow the steps. And when we have the ideal condition, you can see that these two terms should cancel each other out, ideally. So fg0 e to the power of minus tau s should be the same as fs times g model. If the system in the laboratory has the exact same model, then gm is equal to g0 times e to the power of minus tau s. And if that is the case here, you can see that this part is replaced with that, and they will cancel each other out. You will end up in f times g0 divided by 1 plus f times g0 times e to the power of minus tau s. So using Smith predictor means that you're not dealing with the delay part yourself, you're relying on the structure that uses the system model. So it means that if you have a perfect system model in terms of delay, especially in terms of delay, then you can basically use this Smith predictor, which is specialized for systems with delay. And you can see that if we change the, this is the Smith predictor output here, but if we change the amount of delay just slightly, if we have not 2 seconds of delay, but 1.8 seconds of delay, and we're basically using that for the model itself, but G0 is still the same. The amount of delay is still the same. So here's missing comma 2, I guess. Then we get this strange behavior here. So it only works if the delay is exactly known, and if we have a slight deviation in delay, this structure is not going to handle that very well because it mostly relies on that. So everything will mess up. But if you have a model and if you are using the Putty approximation, you're basically also good with that. So it kind of relies on the application and the system itself. You should basically look for both and try to come up with the best controller. It has its pros and cons. As I've told you, if the model is quite good, then this is basically a good tool to use. But there's a slight but here, which is about the structure here. If you think about it, you have to construct an exact copy of the system. So if this is an nth order system, this is an nth order transfer function. Here again, we have an nth order transfer function. And if you use PID, you will have 2n plus 1 in terms of 2 times n plus 1 in terms of the order of the controller plus structure, where where you would just have 1 if you have used the Putty approximation method, because, well, you don't have to have this extra transfer function and this one here, which adds basically more to the complexity. So if you are using Smith predictor, you have to pay for the whole structure here. But if you're using Putty and if it's okay, then you can just go ahead and use that. Well, in terms of preference, I would say you would start with Putty approximation, and if you're not able to reach the criteria or meet the criteria, you would go ahead and opt for maybe the Smith predictor in order to end up in your design. Even that one might not be suitable for that. Then you have to have a better controller, which means that a more complex controller in terms of complexity. So this basically concludes our today's discussion here. We've talked about delay. We've talked about the Putty approximation, which is quite useful. We've talked about the Smith predictor. As far as I remember, we will be talking about the frequency domain in the next week. So see you next week. Have a nice day. And yeah, bye-bye.